So I'm Estelle Hotelier. Good afternoon, everyone. I'm doing my PhD at Naval Group. So here are my supervisors, and we work on intrusion detection systems for industrial systems. And for the presentation today, I will introduce a little bit of our work and what we do. So here is the outline I propose for today. A little bit of context first, then the positioning for our work, the contributions. I will then develop a scenario for a better understanding of what we do, and the results, and to finish, of course, with conclusions and perspectives. So a little bit of context first. So we work on industrial systems. They are called ICS, Industrial Control Systems. They are a set of numerical and physical components acting together to achieve an industrial objective. Here you can see like examples in our everyday life around us of ICS. So electricity production, distribution, transportation, etc. And so all of this system, all of these ICS, they share common characteristics, and they all have the same architecture. And this is the little figure that you can see on the right. So basically, you have the physical process always, and then you have different kind of layers. Different kind of levels, control levels. So first of all, you have the local loop with actuators, sensors, and eventually a local controller. Then you have the PLC level, so programmable logic controller. You then have the SCADA level, so this is the supervisory control level. And so the characteristics that you will always find in an ICS is the fact that the control function is always distributed and hierarchical, as you can see in the figure. The great importance of the physical process, of course. Real-time constraints, you will find hard real-time constraints and soft real-time constraints, depending on the level you are at. And multi-network constraints, so you will find field buses at the lower levels, and you will find TCP/IP networks at the higher levels. And then hybrid dynamic, which is something that will be important for our work, with event-driven and time-driven. So event-driven is something like a rising edge of an actuator or something like that. And time-driven is, for example, like a trajectory or movement that is evolving through time. And so due to this typical architecture of ICS, every ICS have a very large attack surface. And as a matter of fact, they have been the target, like they have been specifically targeted by numerous attacks in recent years. I had to put the well-known and famous Stuxnet attack, which is not the first, but one of the first attack targeting specifically ICS. And there were other attacks in recent years, so like a poisoning attempt in Florida in 2021, and of course in the recent conflict events between Ukraine and Russia, there were a lot of ICS attacks also. And so why are these intrusions possible? I like this picture because it kind of graphically explains why. So it is lack of securing leading to vulnerabilities, and there are a lot of vulnerabilities in every system. So they can be of a lot of different types. So vulnerabilities related to the components of the system, of course. Vulnerabilities related to the overall system itself, related to the usage, or related to the user of the system. So here you can find some examples. And so that being said, I think that we are all pretty convinced that there is a big need for ICS cybersecurity. And so ICS cybersecurity is making a choice of a set of different detection mechanisms. And so if you think again about the picture that I just showed you with the yellow gate, I mean, the yellow gate is great, but we need more. We need to combine different mechanisms. And this is what we want to do with ICS cybersecurity, because every technique can be combined with other technique. They are all, you can combine them. So here, if we take IEC standard, they describe different kind of categories, different kind of protection mechanisms, going from authentication to filtering to encryption and even to physical security controls. In our case, we position ourselves in the bottom right, monitoring and detection tools. And more specifically, what we do is IDS, intrusion detection systems. So here is the definition according to the standard. So a security service that monitors and analyzes system events for the purpose of finding, providing real-time warning of attempts to access system resources in an unauthorized manner. So if you think again about the picture with the yellow gate, we would be the alarm when the burglar or the robber is inside your house. So it's pretty good to know. It's often called an a posteriori technique because you have an alarm when the intrusion has already happened. So in the literature, you can find different types of IDS, two main kinds. So there are the misuse-based one and the anomaly-based ones. In the category of misuse-based, you can find, we often talk about signature-based IDS. So in this category, you really focus on the attacks and you use the knowledge from previously known attacks. Whereas in behavior-based IDS, you don't focus on the attack, you focus on the system. And the main objective is to characterize the normal behavior of a system. So it means that you will be able to detect known attacks. Usually there are many ways of deploying a behavior-based IDS. And there are like some tools that you can use, and most often you can find behavior-based IDS relying on machine learning or behavior-based IDS relying on expert knowledge. And this is what we do, the expert knowledge. So a quick comparison between all of these IDS. So the signature-based one, the behavior-based one relying on machine learning, and the behavior-based one relying on expert knowledge. So the signature-based, they have very efficient results, of course, but as I already said, they cannot detect unknown attacks because they rely on patterns and knowledge of previously known attacks. On the side of behavior-based relying on machine learning, they are very well adapted for great quantity of data. They are, of course, able to tackle great complexity, but they may lack comprehension of the physical process. And of course, there is all the thing with cleaning the dataset and working on the dataset, which can also be a drawback sometimes. And on the side of behavior-based IDS relying on expert knowledge, this time you have a really deep knowledge of the physical process, but the main drawback is the fact that the rules, they are often manually derived, and also you have to be careful with the complexity using this kind of system because sometimes it is not able to scale to bigger systems. So if I want to synthesize what we do, we work on behavioral methodologies relying on expert knowledge. We have a network IDS, so we work both on field bus and TCP/IP networks. We have a specification-based approach that I will detail in the next slides. The detection methodology is based on results from runtime monitoring that I will also develop. And we work on a distributed architecture. So we have a network capture both on field buses and TCP/IP networks, and we work on global and local properties. Concerning the attack typology, we work on process-aware attacks. So it is attacks that rely on really deep knowledge of the physical process. And to give you an example, if you take rudders from a ship. So this is a small replica of a ship. And as you can see, the rudders, they always have to be in the same position. So this is the normal behavior of the system. So you can move them, but they have to be parallel. And an attack would be to put them in opposite position or in a mirror position. So this would be an attack. And to do that, the command that you will send is totally legit. Like in terms of the syntax of the communication protocol, it is allowed to move the rudder. And the problem is the synchronization between the two rudders. So you would not detect any violation in the communication protocol. And this is what we call a process-aware attack and the thing we are interested in. So the contributions. As I said before, we use results from runtime monitoring, also called runtime verification. It is an approach that will extract information from a running system and use it to detect observed behaviors that will satisfy or not a property. So here is a little figure that shows you how it works. The first thing is what we call a trace. It is a finite sequence of observations from the system. In our case, the trace is network packets analysis, just like traffic capture. And then this traffic capture, this observation is sent to a monitor. A monitor is the mathematical object that will compare the observation from the system and a security property in order to give a verdict. And so the third point is the verdict that will verify whether the property is satisfied or not. So if we go back to our approach, we use runtime verification, runtime monitoring, and we will observe and evaluate the behavior of the system at runtime. And therefore, an intrusion will be the violation of a security property of the system. And so if you remember, we are doing a behavioral IDS. And so our goal is to build and to specify the behavior of our system. And we will do that with security properties. And the security properties will be then executed by the monitors to see if they are violated or not. So there are two main phases, the model construction first. So with the building of all the security properties, we extract them from system specification. We use temporal logic and formalisms of temporal logic to express the security properties, such as LTL, MTL, and STL, so linear temporal logic, metric temporal logic, and signal temporal logic. And then this will help us to instantiate our monitors. So this is the first phase. The second one is just at runtime, once you have all the monitors, you can execute you can let the system execute himself and run the monitors and see whether the security properties are violated or not. I will give you another example, more concrete example. So the starting point is safety specifications. So this is the process view. And what we do is we extract the safety specifications from international and industry standards. So to give an example, imagine in a standard you will find a property that says this functioning mode of that control equipment can only occur after that specific event occurred. Then we will translate this safety specification into a security property. So what we call a security property is has a meaning at the network level. The security property is what we call the cybersecurity view. So now it has a meaning in the network level, and we will talk about events, and it will become event B, for example, is observed in the network traffic only after observing event A. Then the formalism view, we will just translate this security property using the formalism I just told you about, using a temporal logic language. So this gives you this kind of property, and this allows you then to instantiate the monitor, which is just an algorithm in the end. So now the attack scenario. So we have a use case. It's a public use case. So it is a replica of a warship, and it has 4 functional chains. So it is like 5 meter long, and you can see on the top picture that it is the physical view with the physical components, and the bottom picture is the control device view. We have 4 functional loops: propulsion, direction, artillery, and energy. We have 5 or 6 PLCs. Just to give you a number. So we work on the direction loop, and more specifically on the local loop direction. So the local loop, you can see it here on the figure. So it is one rudder that is controlled by a motor. The motor is controlled by a servo drive. The servo drive is linked to the PLC by a Modbus RTU field bus. And then we have the PLC, of course. So the attack scenario, we deployed attacks both at the field bus level and at the TCP/IP level, so Modbus TCP/IP and Modbus RTU. We deployed 90 attacks or something like that. I have a slide talking about the attacks later. And on the side of the detection, we also capture traffic at both levels, so at field bus level and at Modbus TCP/IP level. And we do that using ZIC, so the open source IDS ZIC. And the detection algorithms, of course, are also run and executed in order to see if the security properties are violated or not. So here is the simplified architecture, just to show you. We use a publisher-subscriber architecture. So the traffic capture, they are called the workers in ZIC. So we have a Modbus RTU worker and a Modbus TCP/IP worker, of course. They will publish on a message broker, and this will allow our detection scripts and the monitors to subscribe to specific topics depending on what the monitor needs in order to give a verdict. So now for the results part. So in this specific example, so in this local loop, we deployed 33 monitors. We used 2 local loops, so one for each rudder, because one local loop was for one rudder, so we studied 2 local loops. 93 attacks, so as I was saying, both on field buses and TCP/IP networks. And here are some results. So 0 false negatives, 1 false positives. We had some alert overlapping, so this was kind of interesting because we realized that a single comment can trigger multiple monitors. And we have a detection worst case response time of 22 milliseconds, sorry. And on the scalability side, we have a worst case execution time of the detection loop that is linear in the number of active monitors. And what we did is we took the worst case worst case execution time monitor. We executed 800 instances of this worst case monitor to study the scalability. So that's it for the results. And so if I synthesize, I presented behavioral IDS for ICS, relying on expert knowledge. The specification is made out of standards, industry standards. It is a hierarchical IDS, and one of the highlights is that it relies on field bus capture, which is not often the case so far in the literature. And we got promising results and a scalable approach. So for future works, of course, we would like to add a network traffic capture level. So the supervisory control level would be great to have even more data. And we would also like to deploy it on multiple local loops and work on a distributed aspect. So that's it for my presentation. Thank you very much. If you have any questions, don't hesitate. And thank you.
Estelle Hôtelier, merci pour cette présentation. Je vous laisse poser vos questions. La première, madame.
Merci pour cette présentation. J'aimerais savoir si ce que vous avez fait pour Naval Group, vous le vendez également. Est-ce que vous vendez cette expertise ou ce suivi ou cet accompagnement? Ou est-ce que là, c'est juste vous nous présentez ce que vous avez fait parce que Village Recherche est...
Alors, pour l'instant, oui, je suis seulement en thèse, je suis dans ma 2e année de thèse, donc c'est vraiment très général. C'est pas du tout voué pour l'instant à être ni vendu ni rien, mais après, voilà, le but, non seulement c'est quelque chose qu'on aimerait pouvoir développer plus, mais ça, c'est pas à moi de gérer ça. Et pour l'instant, c'est censé être très général et s'appliquer à n'importe quel type de système industriel. Pour l'instant, c'est ça le but et c'est ça qu'on cherche, quelque chose de très général. Voilà.
Alors, si vous ouvrez un groupe de travail, moi j'ai pas mal d'outils, donc ça m'intéresse.
Ok, c'est noté.
Bonjour,
Bonjour.
merci pour cette présentation. Du coup, j'ai une question. Alors, de ce que j'ai pu comprendre sur la détection, c'est que finalement, on analysait ce qui passait sur le réseau pour voir s'il y avait des commandes qui étaient incohérentes, qui étaient transmises. Est-ce qu'il y a d'autres vérifications au niveau physique, par exemple, sur la position des capteurs qui sont aussi implémentés dans ce que vous avez fait, ou c'est seulement en analysant ce qui se passe sur le réseau?
Alors, c'est seulement sur le réseau, donc c'est basé sur le réseau. Mais après, on peut avoir plusieurs types de propriétés. En fait, le fait que ce soit une approche experte, entre guillemets, s'il y a une règle qui nous semble judicieuse, eh ben, on peut déployer cette règle. Et donc, c'est une règle par moniteur. Et donc, il suffit juste voilà, de déployer des moniteurs avec n'importe quelle règle. Le fait qu'on soit au niveau terrain, on peut directement avoir des infos sur les capteurs et les actionneurs, des infos plus fiables que celles au-dessus du PLC par exemple. Et il y a aussi un aspect dont je n'ai pas parlé là, où on va comparer la donnée qui rentre dans l'automate et la donnée qui sort de l'automate pour comparer que ce qui rentre sur le réseau TCP/IP est logique et concorde avec ce qu'on est censé voir en sortie. Voilà, donc on a des choses comme ça. Après, il y a pas mal de règles aussi temporelles. Enfin voilà, à partir du moment où une règle nous semble pertinente, eh ben, on peut l'implémenter. Voilà.
Merci. Estelle, est-ce que vous allez pouvoir vous revenir? Voilà, il y a la caméra aussi qui capte pour la vidéo qui sera retransmise sur la chaîne YouTube du FIC. Autre question?
Bonjour, merci pour la présentation. Je vais rebondir avec une autre question qui concorde avec celle qui vient d'être posée, notamment sur la notion de détection. Vous parliez d'intelligence artificielle, donc je présume avec de l'apprentissage qui se base derrière. Pourquoi ne pas se baser sur des règles de détection comme le fait un CIEM ou un EDR un peu lambda et du coup, quelle est cette vraie plus-value qu'on va avoir avec l'IA?
Alors, non, justement, donc nous, on a fait le choix de ne pas utiliser de l'IA. Pour l'instant, on a des automatisations et des choses qui peuvent être automatisées dans l'extraction de règles, notamment depuis les standards. Mais pour l'instant, on a vraiment fait le choix de ne pas utiliser d'IA. Et la plus-value là-dedans, c'est justement la typologie des attaques auxquelles on s'intéresse, donc les attaques process-aware. Et en fait, on juge que pour l'instant, on a vraiment besoin d'un expert pour pouvoir fixer ces règles qui portent vraiment sur la payload, en fait. Enfin, avec des approches IA, ce qu'on trouve le plus souvent et ce qui fonctionne très bien pour l'instant, ça va être des règles, entre guillemets, sur l'ajout d'un nouveau nœud dans un réseau, des adresses IP non connues, des choses comme ça, ou sur des fréquences. Ça se fait beaucoup et ça fonctionne très très bien sur des fréquences d'échange entre deux machines ou des choses comme ça. Donc ça se fait vraiment super bien. Mais nous, on voulait aller un peu plus loin que ça et on voulait vraiment aller sur le côté process et se dire, par exemple, telle valve va être activée avant telle autre valve, ou des choses comme ça, des choses vraiment du procédé qui vont pas pouvoir être observées. On jugeait que ça allait pas pouvoir être observé de la même manière avec de l'IA. Mais ceci dit, l'idée ensuite, ce serait de pouvoir combiner les deux et d'avoir en fait un modèle expert et un modèle IA qui fonctionnent ensemble avec des histoires peut-être de cycles. Ça, ce serait un future work. Mais en tout cas, il y a vraiment, je pense, une plus-value à combiner les deux. Mais pour l'instant, c'est pas le cas. Dans tous les travaux qu'on a fait, c'est pas le cas.